Continue with the distance vector, and we'll start congestion control. Distance vector routing, we have seen, is based on Bellman-Ford, distributed Bellman-Ford, plus a few additional tricks that we will need to discuss. This picture is illustrating what happens when we go from the theory to practice. The main difference is that the things that we compute the distance to, the nodes to which we compute the distance, are IP prefixes, which are in general not the same as routers. So there's usually not a one-to-one mapping. And secondly, there is of course more than one prefix to which you compute the distance, which means that every router must have a table that gives the distance to all possible prefixes in the world. So this is one of the prefixes called N here. Other than that, so adding this destination N, the algorithm is the same. In particular, for every distance N, a router I will apply Bellman-Ford with the costs that are the costs from itself to the neighboring routers that of course need to be configured. In principle, algorithms like RIP, the one we will see in the lab, sends the updates, so the messages where a node informs a neighbor of its cost to all possible destinations, is often called a routing update, sometimes a router advertisement. In the context of RIP, we call it an update. Is sent periodically, in principle. For example, for RIP every 30 seconds, which is not so frequent, which means if there are changes in the topology, it might take a significant amount of time until new routes are computed. And if a neighbor is no longer present, if a link is broken, it is usually interpreted in the same as having a distance equal to infinity. We'll come back to that detail in a minute. Here's a simple example, a toy network with 4 nodes and a few network prefixes that are around. Assume hypothetically that all nodes boot at the same time, which of course never happens in reality, but that illustrates how things could work. When a node boots, it will of course need to be configured with the prefixes that it will have to distribute into the system. By default, those prefixes can simply be the prefixes of all the interfaces that it has. A router must know those prefixes. So for example, router A has prefixes N1 and N4. Router C has more prefixes, transit prefixes, and M1 and M2 that are local area networks that are stubs. So each of those routers has a local table that essentially says for the local prefixes, in RIP, for example, the distance is equal to 1 if you're locally attached. Other algorithms could have a different convention. You could put 0 here, but in RIP we typically put 1. So that's at the origin, that's what every router knows. And then you run Bellman-Ford, distributed Bellman-Ford. That means that you send to your neighbor all the information you have with the corresponding distance. A knows of 2 destinations, N1 and N4, with cost to destination equal to 1. So it will send this information to all of its neighbors. It will send to B. It will also send to D. I'm showing only how it is sent to B. When B receives this information, B applies distributed Bellman-Ford. Now it needs to apply it for each of the destinations. So it applies it for N1. It compares N1 to what is received. The next hop for N1 was B, so this is not from the next hop. So I look if that gives me a better distance. It does not, so there is no change in the routing table here. For N4, it was not present in the table, which is the same as saying the distance was infinite. So I have now new information. And the new information is again obtained by Bellman-Ford, saying 1 plus 1 gives a distance of 2. This is what will happen at B. Similar things will happen at C. And of course, C will also once in a while send this information to B. So every node will pass all of its table. This is called the distance vector. Vector means it has more than one component. That's why this form of routing is called distance vector routing. And using the update rules, you will, at the end, get this. Every router will have its own table. For example, we can check here that router D has a distance to M2, which is equal to 2, and the next hop is C. Usually in a routing table, we give not only the identity of the next hop, but also the name of the interface on which we reach this next hop, which is, for example, here, given as its prefix N3. That's essentially, there is nothing special. It's just straightforward application of distributed Bellman-Ford. It's worth seeing at the end that we have here 4 routers. Each of the 4 routers has only a local view of the network. For example, here, D knows that in order to reach M2, it needs to go via C, but it doesn't know any further. So the collection of those 4 tables contains all the topology of the network, but by having at every node only partial information. So in that sense, it is a very smart network. Nobody has a global view, but we can reconstruct the global view from local information. We can check what happens when there are failures. The main property of such an algorithm should be that if things change, things can change because a new node is added or a node is removed, or more frequently, something crashes, a link is broken, or a router crashes. For example, assume A crashes. What will happen? Well, in RIP, like in all distance vector routing protocols, all the routes in all tables that are associated with a given next hop will time out if this is not refreshed. So if there has been no update to this entry after some amount of time, which normally should never occur because A periodically sends information to D and B. So this periodic form of information serves as a heartbeat protocol, as a mechanism to check that the neighbor is alive. So when this does not happen because A is dead, those entries that have A as next hop will time out. The timeout, we can interpret it as the same as saying the cost is infinity. We remove, or if you want, we remove them from the table. Now, once in a while, the algorithm continues. So once in a while, C will send its table to D. So now D has lost the information on how to go to N1, which was here, but it will receive from C the information about N1 that D can now use to reconstruct an alternate, a better path, which is now N1 is at a distance 3, which is exactly what happens. In other words, the failure has been recovered, and packets from D to N1 will go this way, or similarly, from B to N4, they will go through this alternate path. So this illustrates that everything seems okay, everything works well. Bellman-Ford, the distributed version of Bellman-Ford, is able to recover from any arbitrary initial condition, which occurred here. We continue to run Bellman-Ford in a topology that has changed, starting from the old state, and we know from the theory that will converge to the new state of the routing table. Of course, this works if the changes are not too frequent. If you change the network topology more frequently than the update of RIP, then it will not be able to follow. Let's look at another case. here is a network with 5 nodes, 5 routers. I've given names like L3, L4, L2, L5 to the links here. And here are the routing tables that I have a bit simplified. So for example, when I am at D, in order to go to little c, which is this entry here, the distance is 3 and the link is L6. That means I should go via this interface, which implicitly means that the next hop is E. So this is what Bellman-Ford will generate after convergence. Now assume we break 2 links at the same time here. For example, we do some road construction and we cut all the cables on some parts of the network. What will happen? Well, at D first, for example, assume D detects the failure first, then the routes C and E that went via interface L6 will be declared as invalid. There are several mechanisms for that. It can be like before, when a router crashed, it can be because D will detect that there is no periodic update sent from E. That's one way to detect the failure of the link. There is usually also MAC layer or physical layer mechanisms to detect that the link is working. So if you break an Ethernet cable, usually the system is able to detect that the cable is broken. But not all link failures would be detected. For example, there might be switches in between. The switches will detect that the link is broken, but the other end would not. So several mechanisms can exist. Either way, at the end, it's the same. It will either be deleted or we mark as the cost as infinite in the table. We will see what in practice we really do, whether we mark as infinite or not. And now let's see how the algorithm continues. So here I'm zooming on the left of the network on what happens between A and D. Assume that A has not yet detected the failure, perhaps because the failure at A will be detected by absence of an update. Then A does its job normally and sends to D its routing table with the distance to C being 3. D will accept this because C and E were previously at infinite distance, so it will take the best that is possible. So therefore, D will think that it can route to C and E via A, which is what Bellman-Ford says. At the second part of this cartoon, assume A also detects the failure. So it will set those 2 entries to little b and c as infinite. And a bit after that, it receives from D this routing table, which contains entries for B and C, distances 3 and 4. Therefore, A will think now it is at a distance 4 and 5 for C and D. Of course, this is wrong in the sense of if we try to interpret those intermediate values as true distances, they are wrong because those informations are based on information coming from here, which are prior to the failure. So this is wrong. But we know Bellman-Ford can live with initial wrong information as long as the network remains stable for long enough for the time it takes for the algorithm to converge. It will converge to the correct thing. Well, more exactly, what will happen if we continue the simulation here for this update? What will D do, or more precisely, what will be the distance computed at D for distance E? I close the poll in a few seconds. And we have two modes in the distribution of answers, 4 and 6. 6 is the correct answer. We need to be careful when applying Bellman-Ford. Bellman-Ford makes the distinction on whether the update comes from the next hop or not, if there is a next hop. Here, there is a next hop for E, which is L3. This link means A. Now, the update comes from the next hop, in which case if the update comes from the next hop, we simply compute the distance advertised in the update, 5, plus the cost of going there, which is 1. 5 plus 1, that gives 6. If the update does not come from the next hop, if A was not the next hop, then we would compare this to the current value, and we would take the smallest of the two. But here we don't take the smallest, so we will take 6. So this is what will happen after processing this update. D will also send similar thing, and A will continue processing, etc. We will see what we have called counts to infinity. Yes, question?
Why was it 5 plus 1 was 5 plus 2?
Because the link costs are 1. The cost to go from D to A is 1, and the cost advertised by A to E is 5. So the cost from me, D, to E is 5 plus the cost of going there, 5 plus 1, 6. That's Bellman-Ford. So this should not be surprising. That's the theory of Bellman-Ford. The network is disconnected, and those two nodes, A and D, are computed distances to prefixes C and E that are the true distances are plus infinity. And we know that in that case, the Bellman-Ford does not converge or goes to infinity, which is the true thing to do. But of course, it's a bit embarrassing. You see that those routers are caught in the loop. They will endlessly compute. How can we fix the problem? We will see that there are several methods, but the first method to fix the problem is to set infinity equal to a large number, which in RIP is a power of 2, because any constant has to be a power of 2 if you want to do efficient C code. And here is 16, which is an evidence that RIP is made for relatively small network. You expect your network to have a diameter that will never be as large as 16. So by default, of course, you can change this default. So the count to infinity will occur if we do nothing else, but it will be at least bounded. When we reach 16, we declare, okay, it is impossible to have such a large value in my network, so I declare it infinity. But we can do better. In fact, it's a bit unpleasant in a network, this behavior of Bellman-Ford. So distance vector routing uses Bellman-Ford, distributed Bellman-Ford, plus a few other tricks. Among the tricks, the one we will see, are essentially route poisoning and also split horizon. Those are their names. But the most important one is route poisoning. Route poisoning is saying if you sense that a distance has become infinite, you immediately send an update to the neighbors with the value of this distance equal to infinity. And by sending it immediately, you will avoid the race, most of the time with high probability, you will avoid the race conditions that occurred before, where you had A that has detected that the thing is infinite, but in the meantime had sent an update that was wrong. And further, when you receive an update that the distance is infinite, for some time you put this, this entry, this destination, in blackout, so you do not process any update about this distance for a few seconds. This will avoid that other routers that have detected the distance, the failure a bit later, that was the case of B in the example before, will not process an update received from A. Split horizon is another rule, so that is very efficient, and except for very rare case where there are race conditions, where two routers send messages at exactly the same time, one before the failure and the other after, which has very little probability of occurring, so in most cases it will avoid the count to infinity. Split horizon is another optimization that essentially is common sense. Is say, if a router A has B as the next hop for a given destination X, then A does not announce this route to B. So A will not say to B, my distance to X is whatever, because A goes via B. So it assumes that B should know better. So you don't inform a neighbor of your distance to a destination if this neighbor is on your path to the destination, because you've learned this distance from this neighbor. So let's redo this simulation, assuming we have those heuristics that are put in place. Here again, D detects the failure. Now D immediately sends an update to A, saying not only that, so in the previous case we sent nothing. We said, I know nothing about C and E. I don't have a distance, so I send nothing. Here we do something differently. We send an update saying the distance to C and E seen from me is plus infinity, which is not exactly the same as absence of a message, as we will see. As we will see now, for example, what are after, when A receives this message, what will be the costs, the new costs that A will assign to, or the new distances that A will assign to little c and little e. I close the poll in 5 seconds. And the majority is right, as always in this country. Why is it? Well, when A receives this update for C and E, we apply Bellman-Ford. And Bellman-Ford says, well, we have to see whether whether the node that's sending the update is the next hop. So for C, the next hop was via L1. So D is not the next hop. So I compare what D is saying about C to what I had before. And I pick the best. Now this is not the best because the distance is infinite. So for C, A will change nothing. A has B that is saying C is infinite distance, but A has another path to C, which has a better, so it keeps it. For E, the story is different because the next hop for E is interface L3, that means D. So A receives an update from the next hop, so it will take it seriously. It will not compare to the existing, but it will add to plus infinity its own cost. Now plus infinity is absorbing. In this algebra, any number plus infinity gives plus infinity. So the cost is infinity. So that means distance to E is infinite, distance to C is 3. So in one step, we have managed to inform A that it has lost its connection to E, which is the correct thing. But it also has lost its connection to C, but it doesn't come from, oops. Okay. Perhaps there's a backup bulb. So it has lost its connection to C also, but this information doesn't come from D, which is normal. And if we continue the simulation, when A detects the failure, ultimately, now after processing, here's the state at A. Now A will detect the failure, so it will declare B and C as being to infinite distance, and it will send the information to D, but it will send to D only the information for which D is not the next hop. D is the next hop for the destination little d, this one. So this one is not passed in the information. So the D information is not repeated here, which would be useless for D anyhow in this case. So we see that, at least in this case, and that's very often the case in many simulations, there is no count to infinity. So we have improved on the behavior of distributed Bellman-Ford. Of course, after some time, those prefixes that perhaps don't exist anymore will simply be removed from the routing table. So you don't keep forever invalid prefixes in routing table. You do some garbage collection after some time. Voilà, those are the essential theoretical elements that RIP adds to the theory of distributed Bellman-Ford. Of course, there's a zoo of a number of other details that you will discover in the lab. Most importantly, for RIP, there is a different routing protocol for IPv4 and for IPv6. It's called RIP-NG for IPv6 because the old name of IPv6 was IP Next Generation. The messages are sent between neighboring routers only, so they are sent one hop and they're sent using UDP. We will see that other routing protocols use different methods. And in principle, we will not do that very much in the lab, but in principle, of course, you require at least some form of authentication between messages to prevent that anybody can connect to the network and pretend to be a router. So you need to have some form of cryptographic means, which at the minimum is the presence of a key in the router. RIP is not used in large enterprise networks, but is very, very frequently used in small networks. It's public domain and free. In enterprise networks, there are variants of RIPs, and the most famous one is the latest version of EIGRP, which is EIGRP by Cisco. It has a large number of optimizations. In particular, it does not have an infinite equal to 16, which means the maximum network size is 15. It has other mechanisms to detect count to infinity. It simply detects loops in the messages. So the routing updates contain an identifier, and you're able to detect that this update is creating a loop. If you start creating a loop, you break the loop using mechanisms that we will not discuss. The main feature that is added to RIP is that the cost of a link is expected to reflect something more useful than simply the number of hops. It uses a formula like, where is the formula? Here. The cost of a link is given by this formula. So this formula accounts for what Cisco calls the bandwidth of the link, so the transmission capability. Another term here, so let's talk about this first term. So the idea is to, when you design a network, if you have links that are high capacity, 10 gigabit per second, and other links that are 10 megabit per second, you give a lower cost to the links that are 10 gigabit per second, because you want the traffic to go there rather than going through the small links. So this is what this achieves. This one achieves something else. It's the capacity divided by 256 minus the load. So the load is how busy the link is, coded on 1 byte, so between 0 and 255. 255 means the link is used 100%, and 0 means the link is not used. So this is an approximation of a queuing formula. If you take the mean queue length in an MM1 queue, you will have a formula that more or less looks like this. And it has the effect of giving a high cost when the load is close to 100% or to the max, 255. And it will give a smaller cost when the load is small. So it will it will penalize links that are heavily loaded. So you'll try to avoid going through links that are heavily loaded. This is dynamic. This is static, this is dynamic. That means there is a process to update the link costs periodically. And then there's something which plays more or less the same role as that, which is the delay. And of course, you need to play with all those and other numbers here. Voila, that's for at least for this part. No, sorry, whoops. This is for the theory of distance vector routing. We'll come back to what it means to have link costs that may depend on the status of the network for EIGRP. For the time being, we can just take them as common sense that says, I want to find the shortest path, that is the shortest path in function dependent on the traffic. Like you do when you try to drive from A to B. If you hear that there's a traffic jam on a given road, you'll try to avoid it. So that's the same idea here. Now in practice, in the internet today, and in all the routers that we have, including the ones you've played with in the existing labs, there are things like IP tables, or in general, per flow tables that exist in addition to the routing tables. Therefore, there are also other mechanisms to update those tables. We will discuss, it's in fact simpler than distance vector routing, but let's discuss for a few minutes what they mean exactly. In principle, an IP router has only one table, called by many people the routing table, called often also the forwarding table. It is the table on which we do longest prefix match by analyzing the destination address of any IP packet. That's what an IP router should do in principle. In the lab, you have seen that it's possible to tweak this a bit. You can cheat, or you can do things like you do in a NAT by adding additional things. This is more and more be done, and this is in particular done in enterprise routers or even switches. If you are Google and you have a big room with 10,000 servers that are interconnected by a network of 200 switches or routers, you may want to influence how the flows are routed where. You may want to do things like give high priority to some mission critical traffic and lower priority to other traffic that can adapt. For example, depending on whether your business is to distribute video, then your mission critical traffic is video. But if your business is to do booking agency type of work, then all the transactions would be, you would like the transactions to have high priority. And if you have people using the same network for watching YouTubes, which is not your job, then you will give it lower priority. So you may want to configure the routing decisions differently for some types of traffic flows. In general, this is what motivates the presence in routers of what is called a per-flow forwarding rule. So a per-flow forwarding rule is something that can take different forms, but in most cases, it is based on a table that contains 3 entries per row. One that is the flow, entries that first describe what the rule is, and priorities. Let's see an example. I think the easier is to explain on an example, which also has the form of a quiz. So here I have the same toy network I've used to explain longest prefix match. And I assume that the first router, R1, has in addition this flow table. So the flow table has typically a flow spec that describes the flow. And then you can have any grep-like type of string. For example, here, the flow spec says input equals 0. So input is the name of an input. On Linux, it would be input equal ETH0, for example. Destination, that's the destination IP address, equal to b.d.anything. That is a rule that you apply to know to which packets we should use this particular action. Then the action can be anything. For example, it can be here output 2, that means this packet you should forward to output number 2. Another rule says anything, destination b.d.star, you drop. And then you have priorities. Now the flow table has, of course, a number of rules. The rules are not necessarily disjoint. Enforcing that rules are disjoint would be a very difficult thing to do. So we put instead priorities. If several rules match the same packet, then you pick the one with the highest priority. And if no rule applies, then you go to the traditional way of doing, which is the IP forwarding table. So a router today, when it receives a packet, it first looks, is there a per flow rule that applies to this packet? If so, I apply it. If not, I will go to the IP forwarding table. If we apply this and we say Lisa and Homer, here and there, are sending packets to this machine called enterprise server, what will R1 do with the packets of Lisa and Homer? Which way will they go? I close the poll in 5 seconds. And the correct answer is none of the above. Why? Well, because one packet will be dropped. The packets from Lisa will match the first flow rule. They arrive on input port 0. They have a destination that is B.D. something. So they will be sent to output port number 2. But this packet, which has the same destination, is dropped. So this router will kill the packets. In fact, if we look at what those rules are achieving, collectively, the two flow rules plus the routing table, we can see that they do the following. All traffic to B.D. something is killed, except if it arrives on input port 0. So in some sense, you are protecting B.D. star, which is where your enterprise servers are, and the only way some traffic can lead to there is if it comes on input port 0. Which is one way enterprise networks are managed today. This is an attempt to limit the damage that security attacks can do. You need to watch very carefully only input port 0. Traffic to B.D. star that is not killed, in other words, that comes on input port 0, goes to output port 2. And traffic to B star that does not go to this protected network is forwarded to output 1. In other words, the link between those two routers here is a private link that is used only for traffic from here to there. All the rest of the traffic going to the B network will not use this link here. Which is, of course, impossible to reach by the IP theory. If you simply do lookup based on the destination address, you will not be able to achieve those things. Now, if you want to run things like this in a network, in a lab, you can do like we did in one of the previous labs. We ask you to do IP table configuration in a few routers, and if you work hard enough, you will be able to get what you want. Now, assume you're an enterprise and you have 100 routers. You need to write the rules everywhere and do some reasoning about rules, inference from the rules to find out what are the conclusions of all the rules. Of course, you don't want to do this by going individually to each of the routers and typing in Quagga or command line commands. So there are dedicated applications. There is another for that purpose. So there is another concept that instead of having the rules manually done in every router, we do them from a central computer, from a central application. This is called software-defined networking. So software-defined networking means we have a central application that downloads the rules into the local controllers at every router. The local controllers are simply translators. They receive the commands from the central controller and they translate them into corresponding entries into the per flow table. This is typically done over TCP connections. So the central controller speaks to all the intelligence of all the routers over TCP connections, which are typically also multi-hops. The central controller is not directly connected to all routers. If you think about it, this is considerably less intelligent than distance vector routing. You have a central controller that has a map of the network, knows what to do, computes the rules that will achieve this. Soon time to do a break. And downloads them in each of the routers. It's not distributed, it's a central solution. It is an apparent contradiction of technologies that the more technology evolves, the more sometimes we go into less intelligent solutions for some problems that we used to solve in the past. I will conclude this session by asking you a question. If I have a network that uses this type of software-defined networking, do I still need RIP? I close the poll now. And the correct answer probably is C. We still need RIP. We still probably. The reason being, unless you put the controller that is directly connected to every router, which means you build a second network for the controller to speak to the routers. But if you don't do this, which probably you don't, because you're building a network here, you have a chicken and egg problem. In order for this guy to speak to this one, then it needs to, the packets that will go from central controller to router R4 need to find a way through the network. So they need that routing tables are present and working in the network. Sometimes you have networks that are very simple, that are, for example, a tree, and you can have simply default routes to go to some specific location, but in general, that is not sufficient. So in general, we should view software-defined networking as something that comes to modify the decisions that are taken by a routing protocol. You still need at least a basic routing protocol for connectivity. Voilà, that's the end of this module. We do a break, and after the break, we change topic and start talking about congestion control. So back in 13 minutes.